Let's spend a couple minutes just reviewing the two hand rules that we've learned to this point. Today we're going to learn about another hand rule called the hand rule for deflection. Let's review the two hand rules that we've learned, the wire grasp rule and then the coil rule, just so that we can make sure that we're good with those before we take a look at that third hand rule. So the wire grasp rule. What's the point of the wire grasp rule? When do we use the wire grasp rule? Well, we know that a moving charge or an electric current generates a magnetic field. Electricity causes magnetism. We use the wire grasp rule not to determine what the magnetic field looks like that surrounds that moving charge, but rather the direction of that magnetic field. We know the shape, that's easy, right? The shape of the magnetic field surrounding this electron, let's say, going into the page is circular. Series of concentric circles that get further and further apart the further I get away from the moving charge. But what's the direction? Well, let's take our left thumb, because it's a negative particle, our left thumb, stick it in the direction of the current. Which way is the electron moving here? Into the page or out of the page? Into the page, represented by that X, right? So we stick our left thumb into the page. Fingers are going to go counterclockwise in this case. When do we use our right hand for this? If we have a positive particle. If this was an alpha particle going into the board, then we would stick our right thumb into the board. Hey, fingers would go clockwise in that case, right? That's the wire grasp rule. Now, we do have situations where the wire grasp rule is a little bit more difficult to do. For instance, if we have something like this, with an electron moving to the right, and we want to find the direction of the magnetic field above and below, and in front and behind that wire. We do the same thing, it's just a little bit harder to visualize. We take, sometimes it's good just to take the pen, literally, and pretend it's your wire. Okay, pen, okay, the end of the pen's pointing to the right. Thumb in the direction of the electron's movement, okay, to the right. Fingers above the wire are into the page. Fingers behind the wire are down the page. Below the wire there, out of the page, and fingers in front of the wire are toward the top of the page. All right? So it's the same thing. Okay, we still got a magnetic field going circular like that. It's just a matter of, can't describe it as clockwise or counterclockwise, and you're looking at it from that direction. The second rule that we learned was the coil rule. What's another word for a coil or a coil of wire? Starts with an S. Solenoid, yeah. Okay. It's a fancy word for a coil of wire. When we have a coil of wire or a solenoid that's wrapped around a piece of steel or a piece of iron or some other ferromagnetic material like this, let's say we've got a battery like this. By the way, which end is the positive end of the battery? Which end is the negative end of the battery? Yeah, the negative is the smaller one. The bigger one is the positive. So the left side is negative. The right side is positive. That means the electric current will go around clockwise like this. Up in the front, down in the back. Up in the front, down in the back, and so on. It's going to go around like this. What's the polarity of this become? We know that there's a magnetic field generated here in this coil of wire, and that magnetic field is going to have a distinct polarity with a north and a south. The question is, which end is north and which end is south? Well, we take our coil of wire, okay, which is a piece of paper. We roll it up like this. We stick our fingers this time in the direction of the current. Okay, so it's opposite to the wire grasp rule. In the wire grasp rule, we stick our thumb in the direction of the current. Our fingers went in the direction of the field. This time we stick our fingers in the direction of the current, and our thumb points in the direction of the field. So our fingers are going to go up in the front or down in the back. Doesn't matter. Okay, up in the front, let's say. My thumb will automatically point which way? You guys can't see my thumb right now, but you can, there, you can see it now. Which way is my thumb pointing? To the right. So the magnetic field inside this coil is going to point to the right. If the magnetic field inside the coil points to the right, then which end is this, south or north? It's going to be north. Didn't we say that the magnetic field goes from north to south? Outside of the magnet, the magnetic field goes from south to north. Inside of the magnet, and that's what we're looking at there, is the magnetic field inside. It's going to go from south to north. We good with that? All right, yesterday we left off taking a look at an application here. We didn't have time to finish that, so we'll spend a couple minutes today looking at that, and then a couple minutes looking at another application, and then we'll go into doing a couple multiple choice questions, and then our new stuff on this third hand rule, the hand rule for deflection. Okay, this is a speaker. Okay, this is Essentially the speaker that you might have in your car, or it could be the speaker that you put literally inside your ear in an earbud, just a different scale, obviously. A speaker doesn't carry sound from your stereo to the speaker. The wire that connects the speaker to the stereo doesn't carry that sound. The wire that connects the speaker to the stereo carries what? Carries electricity. Carries electricity. It carries charges, moving electrons. So how do moving electrons generate that sound, especially the sound that's coming out of your stereo, okay, coming out of your iPod or your iPhone or whatever the case may be? Well, the electrical signal that goes through that wire is proportional to the sound. So in other words, if there's a certain frequency of sound, the electrical signal moves at that frequency. Okay? Now, what does that do? When it gets to the other end, when it gets to the speaker, what does that electrical signal do? Well, we know that electricity generates magnetism. An electric current will generate a magnetic field. Well, we have a magnetic field that's generated by the electric current there. We also have a permanent magnet. I don't know how well you can see that, but you have a permanent magnet kind of surrounds it and goes in the inside as well. So we have two magnetic fields now. A permanent magnet that's always there. If you rip apart a speaker, you're going to see that permanent magnet inside that speaker. And you have this coil of wire that wraps around that becomes another magnetic field when there's a current going through. So what happens is this. When there's a current going through this wire, okay, sometimes it's going this way, sometimes it's going this way, sometimes it's going at a really quick frequency, sometimes it's going at a low frequency. Okay, it's going to create that magnetic field that's proportional to that frequency, proportional to that electrical signal. And as a result of that, it's going to move the permanent magnet back and forth. Okay, there's a magnetic field that we've just produced that will interact with the magnetic field that was already there. And it's going to move back and forth that permanent magnet that's already there. So what? So we got a magnet that's moving back and forth now. That permanent magnet is attached to this cone, okay, this felt cone. When this felt cone moves back and forth with the permanent magnet, it creates differences in pressure in the air right in front of it. If you pull the cone back, it creates a low pressure zone right in front of the cone. If you push it forward, it creates a high pressure zone. What is sound? It's variations in air pressure, right? So that low pressure zone essentially gets transmitted to your ear, and that's what you hear as the sound. So the electrical signal that comes from your iPhone, it ends up producing compressions and rarefactions, if you remember that from Physics 20, okay? Low pressure areas and high pressure areas in the air, which is sound. Does that make sense? So it's all based on, remember what we said when we introduced the idea of Oersted? We said that just about every bit of technology, certainly any electronic technology that we have today, is based on Oersted's discovery. We wouldn't have speakers if electricity didn't generate magnetism, okay? Because we need that magnetic effect within that wire to move the magnets, the permanent magnets, back and forth, which will move the speaker cone back and forth and create that sound. Let's take a look at another one here. Again, not a curriculum objective, just an application that probably won't see. You never know. It's just the idea of going through it so that when we do see a new one on our diploma exam, we're a little bit more able to deal with it. What is this? It's a doorbell. It's a doorbell. It's like an old-fashioned doorbell, not the ding-dong doorbell, but it's one of those ones where you press the button and it rings, kind of like a fire alarm in a sense. Okay? In fact, you could use something like this as a fire alarm. Your switch would just be some switch that was triggered by fire, right? Triggered by heat, or potentially even triggered by hand if you literally pull the fire alarm. So how does it work? Well, right now the switch is off. What happens when the switch is off here? When the switch is off, no electricity is going to flow here, right? This battery is essentially not even there when the switch is off. You got to have a complete circuit in order for the electricity to flow. It's not flowing right now. But what happens when we switch it on? Okay, we press this button. We now have that complete circuit right there. Well, the electricity starts flowing. Which way does it start flowing? Which end is the positive end of the battery? Which end is the negative? The right side is the positive. The left side is the negative. So the electric current is going to start going this way. That electric current will go through this thing that we call the make-break contact. Okay, it flows through here. Okay, I'll trace it out for you because it's kind of hard to see on this diagram. Okay, we trace it out here. Okay, it goes through here, goes through here, goes through here, it goes around here, and back to here. So we've got a complete circuit that looks like that. What's going to happen to those coils of wire as that electricity flows through it? There's going to be a magnetic field produced, right? It's going to produce essentially electromagnets, okay? What was just a simple coil of wire becomes an electromagnet when there's an electric current going through. Okay, now, it doesn't matter which is the north end and which is the south end. It's not really clear on this diagram which becomes north and which becomes south. But let's assume that that becomes north. What does that do? What does that do to this part right here, which is, by the way, made out of steel? What does that magnet do to this green piece of steel? It attracts it. Okay, and as it attracts that piece of steel, it also attracts this hammer. What happens to the hammer? It's the bell. So what do you hear? Ding. You hear ding. That's it. Well, that's not a very good doorbell. Press the doorbell and it goes ding. That's it. Right? Well, what happens when this piece of steel is pulled away from this make-break contact? Okay, this make-break contact right here is pulled away from this piece of steel. The contact is now broken. There's no current flowing through. This disappears. When there's no current flowing through, what happens to the electromagnets? They turn off. Okay, what happens to this? What happens to this piece of steel and the hammer that was attached to this little spring right here? It's pulled back. So instead of being in contact with the bell right now, it gets pulled back. Now it makes contact with the make-break contact again. What happens? The electric current starts flowing again. What happens? This becomes magnetized, pulls it back. Hear another ding. Okay? Okay, now the contact is broken. No electric current. Gets pulled back by the spring. Makes contact. Electric current starts flowing. Gets attracted to the new magnets again. Hear another ding. If the frequency of the electricity that's going through our walls is 60 hertz, and this is attached to our walls, essentially it's not a battery, it's electrically connected to the walls, then this is going to go back and forth, essentially 60 times a second. Okay, so now what we're going to hear is ding, 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 ding. Okay, now that's our doorbell, or that's our fire alarm, as the case may be. Does that make sense? Again, all based on this. If you don't have those magnets, then you don't have this ding, 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 ding. You don't have this doorbell, or you don't have this fire alarm. Okay? This principle was discovered by Oersted, 1819, the idea that electricity generates magnetism. We don't have this if we don't discover that electricity generates magnetism. Go ahead. That's a good question. John just asked, if you didn't hear it, why it needs 2 electromagnets instead of 1. I think probably, John, it's more of a mechanical thing, just to make it in practice work. Maybe if you just have 1 electromagnet, maybe, yeah, I'm not sure. Maybe it doesn't want to, it doesn't want to come over here completely, or maybe it gets off balance or something. I don't really know. Electrically and magnetically, there's no reason why you would absolutely need 2 electromagnets. Maybe the idea is mechanically you need a spring. In order to pull it back, you need a spring that has a fairly high spring constant. Okay? So it's a fairly stiff spring. And if you have that fairly stiff spring, maybe the one isn't a strong enough magnetic field to pull it out from that spring. Not really sure about that. Doesn't really have anything to do with the idea of it, but just maybe the practical nature of it. It's a good question. Would it matter, by the way? Would it matter if we had a North Pole here and a North Pole here? Or should we have a North Pole here and a South Pole here? Would it matter? Sorry, Paige? Would there be a magnetic field between those two? Yeah, well, if you had a north and a south, yeah, there would be a magnetic field, yeah. The magnetic field We'd go this way, sure. Would it interfere with this? No, it shouldn't. It shouldn't interfere. North end would attract this, and south end would attract this. Yeah, north and north. I think you'd still find that it's attracted. I don't think that it really matters there. Okay. If I had to do this, I'd probably err on the side of making one north and one south. Okay, so that effectively this becomes north and this becomes south. There's a temporary magnet there in that piece of steel, but I don't think, to be honest, it would make a huge difference one way or the other. Okay, let's take a look at a couple multiple choice questions. Multiple choice number 66. First of all, I'll ask you to submit that as multiple choice number 1, please. Okay, we got two different responses for this, guys. We got D and B. B and D. So what's the answer here? Well, the question says we want to find the magnets that will repel each other. The magnets that will repel each other. If magnets are going to repel each other, then field lines cannot join up. Right? When field lines join together from one magnet to another, there's going to be an attraction there. It's essentially a north against a south, right, Doc? So we've got to find field lines that don't join up. That means if this doesn't work, we don't even have to identify the polarity of those two magnets. We know that since the field lines join up, then those two poles right here and here have to be opposite poles, and they're going to attract each other. What about the second one? Do these field lines join up? They don't join up with each other, do they? Okay, the field lines oppose each other. They push each other away. So that one looks like it works. What about number 3 here? Do the field lines join up here? Some of them do. Okay, so that's not going to work. Okay, if the field lines join up, then we're going to get a force of repulsion. In this one, field lines don't join up here. Okay, so then that means that we're going to get a force of repulsion. So attraction, repulsion, attraction, and repulsion. We're looking at 2 and 4, which means D is the correct answer. Okay. Now, there were a few people that said B is B and so B, so 2 and 3. So a few people that said these two. This is correct, obviously. This one, I can see why you'd say this one. Okay, I could see why you'd say repulsion there. In the end, we can see this little area right here where the field lines aren't joining up. Well, the reality is we don't always get field lines joining up when things attract each other. Okay, or things. So we don't always get field lines joining up when things attract each other. This field line doesn't join up with anything. There's still a force of attraction there. If you get some of the field lines joining up, it's attraction. You don't have to get all of them. Okay, and clearly in this one, option 3 here, we get some of the field lines joining up from one magnet to the other. So it's got to be attraction. D is the correct answer there. Okay, let's take a look, please, at another multiple choice question here, number 68. We'll submit that one as multiple choice number 1 as well, please. All right, let's take a look at this one now. We got some interesting responses on this one. We have 3 different answers picked, A, B, and D. And for 2 of those answers, we have a significant number of people having picked them. One of them, a few people picked. So A, B, and D. Clearly, all 3 of them aren't correct. Wouldn't it be funny if C was the correct one? No, it wouldn't really be funny at all, actually. It'd be a little depressing. We want to find the direction of the magnetic field point P due to the other 2 bar magnets. We had a question similar to this on our last unit test, but it wasn't magnetic fields, it was electric fields. Remember we had 2 charges. I can't remember how they were oriented. Let's say like this, and we wanted to find the field strength, the field direction right there. Do you guys remember that? I don't remember whether they were positives or negatives and where we were trying to find the field direction, but same kind of idea. Okay, in the end, what did we do? We said the electric field caused by the positive went like this. We said the electric field caused by the negative went like this, right? Away from the positive toward the negative. The net electric field would go like this in between them, right, Travis? So the electric field goes up and to the right. Let's take a look at the magnetic field here now caused by these 2 magnets and kind of look at it in a similar way. The magnetic field caused by the bottom magnet here, okay, this one right here, is going to point up. It points up away from the North Pole. Look at these 2 magnets independently. Okay, the first magnetic field goes away from the north. The second magnetic field caused by this one is going to go toward the south. The net magnetic field is going to go up and to the right, halfway in between, right? Just like the electric field did with the positive and the negative charge. Again, we're dealing with a different field, but there's a lot of similarities between the electric field and the magnetic field. So what's the answer end up being here, guys? D, yeah. We had 29% of you say A. Anybody that said A want to volunteer why they said A? Who said A? Lots of you said it, so. Okay, did anybody want to say why they said it, or it's just I wasn't sure, so I could. Okay, fair enough. So you got a north attracting a south, so there's going to be some kind of, it's going to some kind of pull down there. Okay, fair enough. Does that logic make sense now, though? Yes? Okay. We got one more multiple choice question for you to work on. Multiple choice number 69. Now this one gives people a little bit of trouble in terms of the way that it's drawn here. If you can take a quick look up at this before you start working on this question. These are supposed to be compasses, and the needles of the compasses are on this end. So the needles of the compasses are all pointing, supposed to mean out of the page. Okay, does that make sense? So 4 different compasses, 1, 2, 3, 4. They're all pointing out of the page. We want to know which one's correct there. All right, submit that please as multiple choice number 1 again. All right, let's take a look at this one now. We had most people say C, and a couple people say A. So let's hope that C is the correct answer there. In the end, we've got to take away a couple things from this. First of all, we've got to remember that a compass points in the direction of the magnetic field. So we know that a compass should point in the direction of magnetic field. Fundamental, the definition of the direction of magnetic field, right? The way that a compass points when placed in the field. The second thing is we've got to figure out which way the magnetic field is so that we know which compass is pointing in the right direction. Okay, we've got motion of the electrons through the wire, electron current going up here. If it said conventional current, what would we do? Right hand, right? Because conventional current is the flow of positive charge, even though it doesn't really flow through a wire. Okay, every once in a while, they may throw that little wrench in there. Okay, conventional current, use your right hand. Electron current, use your left hand. So thumb in the direction of the particle. Let's use your pen here, okay, as the manipulative here so that we can figure this out. Okay, thumb in the direction of the current. Fingers, when they're to the right of that wire, are pointing out of the page. In front of the wire, they're pointing towards the left-hand side of the room, the left of the page. To the left of the wire, they're pointing into the page, and behind the wire, they're pointing towards the right. Which compass is pointing in the right direction? Right? Out of the page, to the left, into the page, to the right. Which compass is pointing in the right direction? Well, that's the way we said it, right? Yeah, out of the page on the left-hand side. Or on the right-hand side, sorry. Which one is right? It's 3. Yeah, it's 3. Because we can see that compass is pointing out of the page at that point. This one's also pointing out of the page, but it should be pointing to the left. This one's pointing out of the page, but it should be pointing in. This one's pointing out of the page, but it should be pointing to the right. So the answer is C. Now, you guys did a really good job on that, actually. Okay, probably the best that any class that I've ever had has done. This one always seems to give people trouble, but for you guys, didn't really seem to give you too much trouble. That's good. Good. Okay, we got some check and reflect questions to work on for homework. The ones that I'd like you to do, please, are on page 592, number 1 to 2, 5 to 8, and 10 to 16. 1 to 2, 5 to 8, 10 to 16. You might have a few minutes later on in class to work on this. You might not. I'm not sure yet. Now we're going to see that third rule that I was telling you about. We call it the left-hand rule for deflection. When a charged particle moves, it generates a magnetic field. What if there was already a magnetic field there? Not as a result of that charged particle that's moving, but as a result of the Earth, or as a result of a bar magnet, or as a result of some kind of electromagnet. It doesn't matter what it's from. Okay, we've got a magnetic field that's produced by the moving charge, but we've also got a magnetic field that was already there, caused by something else. We'll call that the external magnetic field. Now we get two magnetic fields. We know that whenever we have two magnetic fields, there's going to be an interaction between those two magnetic fields. There's going to be a magnetic force. What does that magnetic force look like? What's the direction of that magnetic force? This is what we're going to use the hand rule for deflection for. The left-hand rule or the right-hand rule, depending upon whether it's a negative or positive particle. The left-hand rule or the right-hand rule for deflection says this. Essentially, you're going to stick your thumb in the direction of the moving charge, just the same as you did for the first rule that we did, the wire grasp rule. The thumb goes in the direction of the moving charge. But this time your fingers aren't clenched. Okay, your fingers aren't bent. Your fingers go straight out at 90 degrees to your thumb. You're going to have a third variable this time. Your palm is going to point in the direction of the magnetic force. So thumb goes in the direction of the moving charge. Fingers go in the direction not of the field that's caused by the moving charge, but the field that was already there, the external magnetic field. And my palm is going to automatically point in the direction of the magnetic force. Okay, I'll write that out in a little summary here, and then I'll show you an example of how this works. Your thumb points in the direction of the moving charge. That's exactly the same as rule number one, the wire grasp rule. Not the same as the COIL rule, right? But the same as the wire grasp rule. My fingers, this time they're not clenched. This time they're stretched out straight. They're going to point in the direction of the external magnetic field. And what I mean by that is the magnetic field that was already there. The magnetic field, not the one that's caused by the moving charge, but the magnetic field that was caused by the magnets or the earth or whatever it is. The palm of my hand is going to point in the direction of the magnetic force. So I want everybody to take their left hand out right now. Just drop your pens. If you're writing this, I'll give you a chance to write it in a second here, okay? Take your left hand out. Let's say, I want everybody to follow along with this, and I want everybody to move their hand as they need to here, okay? It's a matter of not just seeing me do it, it's a matter of doing it yourself. Okay, that's how you internalize this, is doing it yourself, not watching somebody else do it. Let's say we've got an electron that's moving towards the right side of the room, towards the window over there. Okay, we've got a magnetic field, an external magnetic field caused by magnets, caused by the earth, doesn't matter what it's caused by, but it was already there, a magnetic field that points upwards. We're going to stick our thumb in the direction of the current, which is towards the right side of the room. Our fingers are going to go upwards. Everybody do this, please. Which way does the force point? That way, towards the front of the room, right, towards the board. Okay, let's do another one, okay? We've got a negative particle going towards the floor. A negative particle going towards the floor. We've got a magnetic field that's pointing towards the back of the room. Thumb towards the floor, fingers towards the back of the room, palm points towards the windows, right? Magnetic force is toward the windows. We've got a positive particle going towards the ceiling. We've got a magnetic field that's pointing towards the windows. We're going to stick our right thumb, because it's a positive particle, towards the ceiling. Our fingers stretched out towards the window, and our palm is going to point towards the front of the room. So the magnetic force would be towards the front of the room there, right? Make sense? Let's try this one. Trickiest to the group so far. Okay, let's say we've got a charged particle that's moving towards the right side of the room, a negative charged particle moving towards the right side of the room. Let's say there's a magnetic force that points toward the floor. Which way is the field? Okay, which way is the field? Okay, listen carefully to this again. We've got a charged particle that's moving towards the window. Okay, we've got a magnetic force that's pointing towards the floor. Which way is the field? Warren's got it. Okay, Max has got it here. A few of you have got it. Thumb in the direction of the particle. Usually we say next, fingers in the direction of the field, but we don't know the direction of the field here, right? We're trying to find that. This time we know the direction of the force, which is to the floor. So we're going to say thumb, window, palm, floor, fingers point forward towards the front of the room, right? So my magnetic field would be towards the front of the room. Again, it's like algebra, right? We're rearranging not an equation, but a hand rule. Okay, instead of having thumb, fingers, see which way your palm points, we have thumb, palm, see which way your fingers point. It's not harder. Okay, it's not harder. It's just a little bit different, that's all. Got it? Okay, I'll give you a chance to finish copying that there if you need to, okay? This hand rule, by the way, that we just learned works very, very well if the charged particle is moving perpendicular to the field. If the charged particle is moving 90 degrees to the field. Okay, my thumb and my fingers right now are at 90 degrees to each other. They have to be at 90 degrees to each other for this rule to work. Okay, if they're not, rule doesn't work. That's the good news and the bad news, all rolled into one. Why is it bad news? Well, because if they're not 90 degrees to each other, we can't use that rule. Why is it good news? Well, because that's the only rule we're going to learn for this. So all the questions you're going to see must be 90 degrees to each other. That's not true, actually. They must be 90 degrees to each other or zero. You could get a question where the charged particle is moving parallel to the field. Okay, perpendicular, use the hand rule for deflection. Parallel, the magnetic force is zero. There is no force if the charged particle is moving parallel to the field. So the magnetic force is zero. What hand rule do you have to use? Well, what are you trying to find, right? If the magnetic force is zero, there's nothing to do, right? You just know that it's zero, there's no direction. So you'll either use the hand rule for deflection to find the direction of the force if they're perpendicular, or it's going to be a zero force and you don't have to do anything in that case. Yeah, let's take a look at an equation that describes the force now. Not just the direction, but for the first time this unit, an actual equation that describes something for us. Okay, the value of the magnetic force, Fm, is equal to Q times V times B. Let me make this a little bit bigger for you so you can see it better. QVB. Fm obviously stands for magnetic force, and that's going to be measured in newtons. Q stands for the charge, and that's going to be measured in coulombs. What do you think V stands for? No, it's not a direction. V stands for not velocity, but you're close. Speed, yeah. And that's going to be in meters per second. B, we talked about this already earlier in the unit. B stands for magnetic field strength. And the units for magnetic field strength are Tesla. Remember we talked about the various magnetic fields. The Earth's magnetic field was 10 to the minus 5. A bar magnet, 10 to the minus 2. An MRI machine was 10 to the plus 1, about 15 Tesla. What does this little thing right here mean? This little upside down T. It's perpendicular. Okay, I told you the hand rule is only valid if the charged particle is moving perpendicular to the field. Well, so is the equation. You can't use this equation if the charged particle is not moving perpendicular to the field either. The good news is, if you get a question where the charged particle isn't moving perpendicular to the field, then it will be moving parallel to the field. And if it's moving parallel to the field, what's the value of the force? Sorry? Zero. So there's no equation to find it, right? If the magnetic force is zero, then that's your answer. If you get a question where you have to use the equation to find the force, this is the equation you're going to use, okay? All right, let's take a look at a little question here now. 12.1, page 599. If you don't have chapter 12, download it. Now's the time to do that, okay? Going into a new chapter here. An electron is traveling at 3.2 times 10 to the 5 meters per second, which is a pretty typical speed for a moving charge, right? 10 to the 5, 10 to the 6, usually those kinds of speeds, right, Josh? We have a magnetic field of 2.2 times 10 to the minus 1 Tesla, which is pretty strong magnetic field caused by these bar magnets, but there are 2 bar magnets, right? We want to find the direction of the magnetic force. We want to find the magnetic force, which includes a magnitude and a direction, since force is a vector. Okay, let's get the magnitude first. Hey, the good news is we see that we're perpendicular. We know that the equation that we just learned is a perfectly valid equation. If they weren't perpendicular, then they'd have to be parallel. Okay? Later on, if you take engineering or something at university, you will see questions where they're not perpendicular or parallel. And to be honest, they're not very much harder. But we don't have to do them, so we won't. This one is perpendicular. If it was parallel, which is the other possibility that we could see, the force would be 0. We know that equation is valid. We know this is the speed. We know this is the magnetic field. It's an electron, so we know the charge. We know the mass of the electron. Let's find the value of that magnetic force. QVB. It's 1.6 times 10 to the minus 19 coulombs times the speed of 3.2 times 10 to the positive 5 meters per second times the magnetic field of 0.220. So we get 1.13. 1.13 times 10 to the negative 14 newtons. That's a pretty small force, right? But we're also talking about the force on an electron, so it doesn't take much force to move it, right? 1.13 times 10 to the minus 14 newtons. What about the direction of that force? Okay, let's do that now all together here, okay? The electron, they've got it drawn, and they're trying to do a three-dimensional thing here. Sometimes it's easier if we just draw it as an X, meaning into the page. That's what they mean here, though, into the page. So the electron is moving into the page, left thumb into the page. My fingers should point in the direction of the magnetic field. That's from north to south, right? Always away from the north toward the south. So fingers, thumb into the page, fingers from north to south, palm points which way? Don't say up, say up the page or toward the top of the page, because our frame of reference here is the page here, right? So it's 1.13 times 10 to the negative 14 toward the top of the page. Make sense? Doesn't seem like any of the 3 hand rules that we've learned so far are that crazy hard, right? The challenge that people have in this unit, if they have a challenge, is keeping those hand rules straight. It's not how do you do hand rule number 1 or how do you do hand rule number 3. It's keeping straight hand rule number 1 and 3 when we see questions involving both of them at the same time. And we'll work on that as the unit goes on. I want you to take a quick look, please, at the practice problems that go along with that, page 599. But let's focus on question number 1. Why do I not want you to do question number 2? Sorry? No, it's not too easy for you. It has an angle, right? 30 degrees. Okay, we could do that. I could make a slight modification to the equation that I taught you to make it valid for a 30-degree angle. But we don't have to do that, so we won't. Nope, no, not at all. So we'll deal with questions that are always either perpendicular or parallel. So take a look at question number 1, see what you can do with that one, okay? No issues with question number 1? Everybody's got it? Okay, let's take a look at one more example and then we'll wrap it up for the day here, okay? This one says a carbon ion. We don't know anything about a carbon ion, but they tell us something about it, right? It has a mass of 2.01 times 10 to the negative 26 kilograms and a positive charge of magnitude 1.6 times 10 to the minus 19. Enters the region of an external magnetic field of this value, 6.35 times 10 to the minus 5. Find the perpendicular speed, perpendicular, that's good because the equation that we've learned is valid, at which the magnetic deflecting force will balance the gravitational force such that the carbon ion will travel in a straight line. In other words, there's a magnetic force that acts on this carbon ion. There's a gravitational force that acts on this carbon ion. We want those two forces to balance so that it goes straight through, so that it's not deflected. Let's just double check that this would work here, okay? The gravitational force would pull down on the carbon ion. Which way would the magnetic force act? Carbon ion is, it's a positive charge, so it's going to be right hand. Okay, right hand, right thumb into the page in the direction of the particle. Fingers from north to south, the palm would point upward. The magnetic force would be upward. Could those balance each other? Yeah, sure, if they're the right values, they could. So what are you going to do here? What are you going to do? Yep.
Find the force of gravity.
Okay, you could absolutely find the force of gravity acting on the ion first. And what would you do with that? Make that equal to the magnetic force? Yeah, absolutely, absolutely. Or what you could do is just say the magnetic force is equal to the force of gravity. That's effectively the same thing, right? Okay, if you calculate, Mac, the force of gravity, and then Tanner, you set it equal after that to the magnetic force, great. Okay, if I choose to set them equal to each other right off the top, it's the same thing. So we say QVB, this equation we know is valid because they're perpendicular, equal to m times g. We're solving for speed here. So V is equal to mg over q times b. Let's plug in our numbers here and see what we end up getting. The mass was 2.01 times 10 to the minus 26 times 9.81. We'll just make g positive there. Q is 1.6 times 10 to the minus 19 times 6.32 times 10 to the minus 5. You get 1.95 times 10 to the minus 2 meters per second there. Is that okay? Listen, this is the first time we're encountering something like this where these two forces have to balance. We will encounter that from now on often. When something is undeflected, when something is in two fields, when something experiences two forces, but it doesn't change direction, then those two forces have to balance. If they balance, set them equal to each other. Okay, if it says something's suspended, if it says something's undeflected, if it says something travels straight through, then set two forces equal to each other, and 9 times out of 10, one of those forces will be gravity. Okay, let's take a look at these two questions. We won't worry about question 2b yet. We'll focus on that one tomorrow. So question 1 and 2a, work on those over the next couple minutes. And then if you finish those up early, then you can finish the check and reflect or work on the check and reflect questions that are due for homework tomorrow as well.